I went to NASA and said F equals ma. They kicked me out. So F equals ma. Force equals mass into acceleration. Newton's second law. That is how you learn it at school, right? But to be honest with you, F equals ma is not Newton's second law. Okay, it's rather one special consequence of Newton's second law, which is more abundant and can be commonly experienced in our nature. The way Newton formulated the second law was that he just said the force applied is directly proportional to the rate of change of momentum. So our force is directly proportional to the rate of change of momentum. Okay, so P over here is the momentum and dP by dt just means rate of change of momentum. Okay, so to change this proportionality sign to equality, you multiply it with a constant k times dP by dt, right? Now let me tell you that Newton was the first one to define force in physics. Force in physics did not exist before this law. Okay, so Newton had the liberty, had the freedom to choose any units for force. Okay, and like any other intellectual would do, Newton just chose those units which makes this value of k 1, and those units were Newton. Of course, the SI unit of force is Newton, right? So whenever you measure force in Newton, the value of this k is 1. So you can simply write force equals dP by dt, right? This is because Newton had the freedom to choose any units. He chose units in which the value of this k becomes 1, okay, just for simplicity. Now proceeding by the same lines as you would in your school, you say that this momentum is defined as the product of mass of a body into its velocity, right? You can write momentum as mass into velocity, and substituting that over here, you'll say d, substitute the value of p, which is mv by dt. You also know that mass of a body is constant, right? It does not change with time, so you can take that out of the differentiation sign and you're left with dv by dt. So force equals m times dv by dt, the rate of change of velocity, which is nothing but acceleration. So from here, you can imply that force equals mass times acceleration. So why is this a lie? But if you see over here, we made a small assumption, right? We said that the mass of the body is constant. But come on, the mass of a body is always constant, right? Does it vary with time? It does not. Or does it? In fact, in some special cases, it does. The mass of the body does vary. And here we have one such special case, which is rocket propulsion. And by the end of this, I'm going to show you how F equals ma in a way is a lie. Okay, so let's get over here. You can see initially we have a rocket which has a total mass m, including the mass of the fuel. The total mass of the rocket along with that of the fuel is m, and it is moving with a velocity v. Okay, after a small interval of time dt, now mind you, dt is a very tiny interval of time. Okay, so after that tiny interval of time dt, the rocket has burned dm amount of fuel. Okay, so its mass becomes m minus dm. Okay, so dm amount of fuel is being burned. Okay, and this burning fuel is thrown in the opposite direction, this direction of the velocity of the fuel. You can see that it is opposite to the direction of motion of your rocket, right? And it is moving with a velocity u, okay, and in the opposite direction, of course. And you can also see that the velocity of the rocket has now increased. Of course, it has burned some fuel, so its velocity will obviously increase, right? There is an acceleration over there. Okay, so you can see that the velocity has increased from v to v plus dv. Okay, so dv is the increase in the velocity. Okay, so let's run a little bit of math over here and we'll be able to prove that F in a way is not equal to ma. Okay, so let's see for the initial momentum. So initial momentum, you know that momentum is defined as the product of mass into velocity, and initially you can see that it's basically m into v, right? The mass of the body into its velocity. So initial momentum is m into v. Okay, let's come to our final scenario and look out for final momentum. So final momentum will be momentum of this rocket as well as the momentum of fuel. Okay, so momentum of rocket is m minus dm. Okay, its mass has changed. As you can see, it has burned some fuel, dm amount of fuel, right? So m minus dm into its velocity has increased. Okay, and now you also have to add the momentum of fuel, right? So you add dm times u. Now mind you, momentum is a vector, right? You can see that we have considered the velocities in the upward direction to be positive, so this velocity is in the opposite direction, so you have to put a negative sign over here. Okay, this v is in the upward direction, v plus dv is also in the upward direction, so by convention we have chosen them as positive, so u, which is in the opposite direction, should be negative because momentum is a vector. Okay, so let's simplify this final momentum term, and we can get, here we'll get mv plus mdv minus vdm, okay, and minus dm dv. Okay, actually we can neglect this term dm into dv because basically it's small, but let's just keep it. Okay, and finally we have minus u dm, okay, or dm into u, or dm u dm, whatever. Okay, and now we can take this dm common from these three terms. Okay, so mv plus m into dv, and here we have dm common, so we are left with v plus u. Okay, we have taken minus dm common, so v plus u plus dv. Okay, so v plus u plus dv is what we are left with. Okay, so this is the final momentum on simplifying, and this is the initial momentum. Okay, now we can find the change in the momentum dp. You know where this is going, we are going to find dp, then we are going to divide it by the small interval of time, dp by dt, and that is nothing but force, right? We know from Newton's second law that force is equal to dp by dt. Okay, so we are finding the change in momentum over here, so we can find the change by just finding the difference between the final momentum and the initial momentum. So dp will be given as final momentum minus initial momentum, so this term minus this term. So you can see that mv is common over here, so mv and this whole thing minus mv, so this and this will get cancelled, and you will be left with m dv minus dm into v plus u plus dv. Now this thing might seem complex, v plus u plus dv, but let me tell you that it is just the relative velocity between this fuel and the rocket. Okay, don't believe me, let's consider this velocity as va. Okay, the velocity v plus dv, the velocity of the rocket in the final state is va, and the velocity of the fuel in this final state is vb. Okay, tell me what is vab. For those who don't know VAB is the velocity of A as seen by B, the velocity of rocket as seen by your fuel. Okay, so it has a simple formula which just says VAB equals VA minus VB. Okay, of course you have to substitute it vectorally. Velocity is a vector, guys. Okay, so velocity of A we know that V plus dV, and in the upward direction, so it's positive, minus velocity of B. Velocity of B is u, minus u in the opposite direction, right? So minus u. You can see that this will give us V, and this minus and minus will become plus, V plus u plus dV. So VAB is nothing but that term V plus u plus dV, right? And we can just call it VAB, or we can call it the relative velocity between the rocket and our fuel, right? I know a lot is going on over here, but yeah, finally we are going to prove that F is not equal to ma. Okay, so yeah, so in place of V plus U plus dV, we can just substitute V relative, right? So m dV minus V relative times dm. Okay, in place of V plus U plus dV, we have substituted V relative. Now let's proceed our discussion further. So we have found out that dP equals mdV minus the relative velocity between the fuel and your rocket times dm. Now we also know that dP by dt is force, right? So let's divide this dP by the small time interval dt. So dP by dt, and do it on the right hand side too. So dV by dt minus V relative into dm by dt. So you can see that this is nothing but force. force equals mass into acceleration minus v relative into dm by dt. So force equals mass into acceleration minus something. Force is not equal to mass into acceleration. Rather, force equals mass into acceleration in a way is a lie. Now, some of you all will surely point out that this term can be called your thrust force, right? So, thrust force can be written as V relative times dm by dt. Okay, so you can write F equals ma minus the force of thrust. In place of this, you can write force of thrust, right? So you can bring this on the side, on the left hand side. So you can write force plus this force of thrust equals ma. So again, you can write F net equals ma. So is it really a lie? Now it is just a play of terminologies. Okay, so if you consider the fact that your mass can vary too, and if you include your thrust force within the F net and say that F net equals ma, then you are right. But if you don't include the fact that mass can vary too, and you do not include the thrust force in this F net, and if you say F net equals ma, then you are wrong. And that's all for today's episode. I hope you enjoyed it. I'll see you soon in the next video. Bye bye.